The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: Agriculture, Earth and Environmental Sciences, Engineering, Chemistry and Physics, Life Sciences, and Mathematics, Statistics and Computer Science. Engineering is offered on the Howard College campus, Agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westwood campuses. Exceptions are Agricultural Engineering, which is offered in Pietermaritzburg, and Geology, which is offered at Westville only. And to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering, and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general botany, hydrology, that in scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the end of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for poultry science, horticultural science, and agricultural engineering. Adjoining Upalinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCON-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering, and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering, and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. College has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research, Environmental, Coastal, and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for undergraduate and postgraduate students. One of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines, plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor and the laser, and is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the past. The highly successful Unite Engineering program And the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development, and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering, and technology through exhibitions, festivals, and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do not meet the minimum requirements, access programs are available. Additional information and brochures can be obtained from the contact information accompanying this video. The College of Agriculture, Engineering and Science is proud of its contribution to the university, the region and the country.
UKZN is one of the best. I deeply understand it's one of the best in South Africa. So for me, there was no other institute that I would have preferred other than UKZN.
We have the best facilities here in terms of laboratories, in terms of equipment, in terms of human resources, in terms of literature.
The UKZN is one of the best universities in the country that teach agriculture and natural sciences.
What I think is good about this college is the level of international collaboration that we have. We have friendships with universities all over the world, which means that we're keeping up to a great international standard.
UKZN has got much more facilities and it's recommended worldwide to do your science studies here. Life begins here.
We continually strive to be academically excellent, innovative in research, and critically engaged with society. We invite you to join us or work with us to be part of this exciting team.
Hi everyone, glad to see so many people have made it. So today we're going to be going through some patterns. We'll do that for about an hour, and then after a short break, we will then go on to some functions work. Okay, so let's take a look at the first question here. So we've got 4 terms of a quadratic pattern. So we should have some idea in mind of what that really means. Okay, so the first question here, write down the value of the 5th term. So let's just start off by writing out the terms. So we have 15, 29, 41, 51. Now we know that with quadratic patterns, it doesn't have a constant first difference, but there is a constant second difference. So the idea is to find the second difference, and then we can extend the pattern from there. So for the first bit, we're going to have 29 minus 15, that'll give us 14. 41 minus 29, it'll be 12. Then we're going to get 10. Now, if we look at the second difference, we will see that we get minus 2, and this needs to continue. So we can extend this. We know that the next term will be minus 2. So what is the next term for the first difference? Well, if we're going down by minus 2 each time, then the next one should be 8. Now, if that one's 8, we can then find the next term just by extending that across, and that will be 59. Okay, so that's how we can find the next term. We just extend the pattern using our second difference and the first difference. Okay, for the next question, we need to find the general expression. So instead of just extending the pattern term by term, we want the general pattern for each term in the sequence. So it's pretty easy to do. There's a set way of working this out. So all you need to remember is that 2a is going to be this first term over here, minus 2. And we can use that to find a. So in this case, a is just going to be minus 1. Then we have 3a plus b, that's going to be equal to 14, which is our next term over there. And then we use our previous result to get the next result. So we're going to have minus 3 plus b is equal to 14. So b must then be 17. Okay, and then for the last one, we have a plus b plus c, and that's going to give us the first term from the original sequence. Okay, so the first term of the quadratic sequence in this case. Now, this is going to be equal to 15. And again, we use the previous results to find the next one. So we know the value of a, that's minus 1. We know the value of b, that's 17. And we're trying to work out c. And all of that's going to be equal to 15. Okay, so that's 16 plus c is equal to 15. A little bit of working, c is equal to minus 1. Now, it's pretty easy to get our a, b, and c, but I just need to give you a little warning that because the next result always depends on the previous. So finding b, we need a, finding c, we need a and b. Make sure you check your work at each step. So when you find a, make sure that that's correct. Because if you substitute an incorrect a value, you're going to get an incorrect b value and then an incorrect c value, and then everything is just a mess. So make sure you check at each step just to be safe. Okay, so now that we've got these three, we can write down Tn is an squared plus bn plus c. Okay, that's always the case. It's always standard like that. So Tn is equal to, a is minus 1, so we just get minus n squared. B is 17, so we just get 17n. C is minus 1, so we just get minus 1. Okay, so that's going to be the general pattern. Okay, you plug in any n value and you get your Tn value. Okay, so really not too bad. Now, if you do have any questions while I'm going through these, please just put them in the chat. Okay, so you type your questions out and there'll be someone available to help you with that. Also, during our little break after an hour, if you have any questions then, you can put them in the chat and we can have a look at those as well. Now, please keep your questions related to what we're covering. If you do have questions unrelated to what we're doing, there is a dedicated email that you can use. Okay, so everyone should have that link there. Just send them an email and someone should help you out there. Okay, let's take a look at the next one. Okay, so we've got ourselves a geometric sequence. So whenever you hear the word geometric, you know that there's a constant ratio that gets you from one term to the next. So from the first term to the second term, you multiply by this ratio. From the second term to the third term, you multiply by the same ratio. Okay, just keep that in the back of your mind. So 2.2.1. Determine the value of R, which is this common ratio. Okay, so 2.2.1, we want to find R. Now, R, we can do T2 over T1, or we could do T3 over T2, or we could do T4 over T3. It doesn't matter, because remember, it's a common ratio. So you take any two terms, consecutive terms, you take the ratio, and you get yourself the R value. So in this case, let's look at T2 divided by T1. So in this case, R is going to be T2, so minus 18. T1, that's 36. So we get minus 1/2. Okay, which makes sense because if we look at the first term going to the second term, we see that it's decreasing. And from the second term to the third term, it's also decreasing. So we expect that the ratio should be some kind of fraction. Okay, which it is. Okay, 2.2.2. Calculate n if Tn is equal to 9 over 4096. Okay, so with this type of question, we just need to know the general formula for a geometric sequence. We plug in Tn because we know what that is. And then with a bit of work, we can then solve for n. So we know Tn is equal to AR to the n minus 1. Okay, that's the standard formula. Okay, so Tn is equal to A, that's our first term, that's going to be 36. R, that's our common ratio, we just found that, that's minus 1/2. And n minus 1. Now we want this to be equal to 9 over 4096. And the goal is to find this n that's in the exponents over here. So we want to work that out. Okay, so we need to try and isolate that n if possible. So the first thing we need to do is divide through by that 36. We want that on the other side. So we're going to get minus 1/2 to the n minus 1 is equal to 9 over 36. We're going to get a 4 on the bottom. So that's 1 over 4 times 4096. Okay, getting better. Now, on the left-hand side, we see that the base of this exponent term over here is 1/2. Okay, or minus 1/2, but that doesn't really matter. We've got the half there. On the right-hand side, we've got this crazy fraction. Now, if we want to find what the exponent is, the best way to do that is to make sure that the bases on the left-hand side and the right-hand side are the same base. Okay, because then we can easily compare the exponents. So if on the left-hand side, we've got a half, on the right-hand side, we should also write that as a base 1/2. So we're going to get minus 1/2 to the n minus 1 is equal to, okay, with a little bit of work here, we can write that as a half to the power 14. Okay, so now that we've done that, we can now compare the exponents. So we're going to have n minus 1 is equal to 14. So n is equal to 15. Okay, so we get ourselves the value of n. So the term with this value over here is the 15th term. So the term with value 9 over 4096 is the 15th term. Okay. So that's how we found that. And again, if you have any questions while we're going through this, please just put them in the chat and then we can have a look. Okay, so let's see what's up next. So 2.2.3, calculate S infinity. So what that means is we're taking the sequence, so all the individual terms, and we want to sum them up all the way up to infinity. Now, you should always keep in the back of your mind that this S infinity only works if the ratio, this value R, is a fraction. Okay, it can be a positive or negative fraction, but the idea is that it must be a fraction for this to work, which is good because in our case, the ratio is minus 1/2. So S infinity makes sense and we can work it out. So let's see how we do that. 2.2.3. So we want to calculate S infinity. Now there's a standard formula for this. It's going to be A over 1 minus R, where R is that ratio we were talking about. A, that's still your first term. That's going to be 36. And then we have 1 minus. Now, just keep in mind, it's going to be minus 1/2. So minus 1/2. So that's going to be 36 over 1 plus 1/2 And we can simplify that down to just 24. Okay, so we see that the infinite sum or the series of all of these terms is 24. Okay, so that's not too bad. You just need to know how to use this formula over here, and just be careful with the sign over here. If your ratio is negative, like -1/2, it's going to be minus -1/2. So that's going to end up being a plus. Okay, so just check your signs when you're substituting. Okay, but the rest is pretty straightforward. Let's have a look at the next one. Okay, it looks a bit messy, but let's have a look. Calculate the value of, and then in the numerator, we've got T1 plus T3 plus T5. It looks like we're summing up all of the odd terms. Okay, because we've got 1, 3, 5, 7, all the way up to 499. So those are all the odd terms. And by odd terms, I mean that n is odd. And then if we look at the denominator, we've got T2 plus T4 plus T6, all the way up to T500. And that looks like all of the even terms. And again, by even terms, I mean that n is even. Okay, so it's this alternating behavior. We've got the T1 at the top, then T2 at the bottom, T3 at the top, T4 at the bottom. So we can't directly sum these up, because if we wanted to sum them up, they need to be in consecutive order. We need T1 plus T2 plus T3 and so on. But we're skipping terms in the top and we're skipping terms in the bottom. Okay, so directly summing it up, that's not going to work. We need another plan. Okay, so let's have a look at that. 2.2.4. Okay, so let's just rewrite what that said. So it was T1 plus T3 plus ... all the way up to T499. So that was all the odd ones. And then in the bottom, we had T2 plus T4 plus ... plus T500. Okay, now the fact that we're skipping terms means we can't evaluate the sum directly. But we can still attempt to evaluate the sum. So let's substitute some terms and see what we can get from that. So T1, that's going to be A, that's just our first term. T3 is going to be AR to the 3 minus 1, that's just AR squared, plus ... T499, that's going to be AR to the 498. Because remember, we always have to subtract the 1. It's AR to the n minus 1. Okay, so that's the top. And then at the bottom, we've got T2, that's going to be AR, and then AR cubed. And this is going to go all the way up to AR to the 499. Again, because it's AR to the n minus 1. Now, we notice something. If we look at the top, we've got AR squared, and we end with AR to the 498. In the bottom, we've got AR cubed, and we're ending with AR to the 499. Each term in the bottom has R with one more exponent. So the first term at the top, that's A times R to the 0, if you want to think of it like that. In the bottom, we have AR to the 1. In the top, we have AR squared. In the bottom, we have AR cubed. So there's always this extra factor of R going on in the bottom. So let's try and factor that out. So in the top, we still have A plus AR squared plus ... plus AR to the 498. But in the bottom, we noticed that there was that extra factor of R. So let's take that out. So we're going to have R, and then we're left with A plus AR squared. That's looking familiar, plus AR to the 498. Now, take a look at the top and look at the bottom. Those two sums are exactly the same. So we factored out R, And now we see that those are the same. So we can just cross out the top one, cross out the bottom one. So that cleans up really nicely. And we're just left with 1 over r. Okay, so it was quite a mess at first, but once we took out the factor of r, everything just canceled. Now, remember what r was. That was back here. R was -1/2. So we take the reciprocal of that, we get ourselves -2. Okay, so not too bad. So if you're ever in doubt with these types of weird sums, so like we've got the sum of odd terms divided by the sum of even terms, my suggestion is write out a few terms and see if there's any pattern involved. So here we saw that the bottom term, bottom denominator was related to the top because it was just multiplied by r. And we noticed that right away after writing out a few terms. So just a little bit of advice. Okay, especially with these types of sums. When you're stuck, write out a few terms. And look for some pattern. Okay, so there's always going to be some pattern to simplify the question. Okay, so that's the key idea here. Look for this pattern, look for some similarities that can help you simplify your working. Okay, but whenever you're stuck with something with patterns, write out a few terms and maybe you'll start seeing the pattern a bit more clearly. Okay, let's have a look at the next one. Okay, we're done with all of that. So not too bad, going through quite quickly. Let's have a look at
there's 2 questions in the chat about the previous question.
Let's have a look here. Why did we say the bases are the same? The negative. Oh, okay, sure. Let's have a look at that. Okay, the bases are the same because if we look here, n is odd. So we've got here odd n. So this -1/2 to the n -1, we can write this as -1 to the n -1 and half, sorry, it's a bit messy, to the n -1. This -1 we can multiply inside and that will change it to a plus. So whenever your n is odd, n -1 will then be even. Okay, so that will be even. And then if you have any negative something to the even power, it's going to end up being even. So we've got the minus on this side, we raise it to an even power, and that cancels with that minus there. So you can think of something like -1 squared being just 1. Okay, so that cancels out the negative there. Okay. Or 2.2.2, where did the 4 come in the denominator? Let's have a look at that. Oh, that 4 over here, just make a little note. This 4 came from the fact that we were dividing by 36. So we've got 9 over 36. And then I just simplified that down to a 4. Okay, I hope that helps. Let's take a look at the next set of problems. Okay, question 3. So the first 3 terms of an arithmetic sequence. Okay, so as soon as you see that, you should be thinking to yourself, common first difference. That's the defining feature of an arithmetic sequence. Okay, and we've got a couple terms here, 2p plus 3, p plus 6, and p minus 2. Okay, so we don't know what p is, but for the first question here, it says show that p is equal to 11. Okay, so let's write out the few terms that we know and see what we can do from there. So 3.1.1. So we've got 2p plus 3, p plus 6, and p minus 2. Now, we know that this is an arithmetic sequence, so it's got a common first difference. So if we take T2 minus T1 or T3 minus T2, we should be getting the same answer. So let's do that. So we're going to take our p plus 6, or the T2 term. So we have p plus 6 minus 2p plus 3. And that's going to be equal to, well, we can take the next two terms, p minus 2 minus p plus 6. So we can think of this as taking T2 minus T1. That's going to be a common first difference. Or we can take T3 minus T2. That's also a common first difference. Since they're common, they better be equal. Now we can just solve for p. So we're going to have p plus 6 minus 2p minus 3 is equal to p minus 2 minus p minus 6. Okay, then we end up with canceling some things out, taking some things over. We get minus p, okay, from the left-hand side. And if we take all the numbers over to the other side, we get minus 11. So p is equal to 11. Okay, which is what we wanted to show. That's good. 3.1.2. Calculate the smallest value of n for which Tn is less than minus 55. Okay, so we know that this sequence has a number of terms going along. At some point, we will reach a term that is close to minus 55. Okay, maybe not exactly, but close to minus 55. And then after that point, we're going to get terms that are less than minus 55. We want to find the first term after that point. So the smallest one. Okay, so let's have a look at that. So 3.1.2. Okay, so let's write out our sequence again. So we have something to work with. So we have 2p plus 3, p plus 6, p minus 2, and that's going to continue. If we substitute in p, because we know what that is now, we're going to get 25, 17, and 9. Okay, so it's decreasing. And again, it's going to decrease to end up being minus 55, and then it's going to be smaller than minus 55. We want to find the points at which it becomes smaller than minus 55. Okay, so what's our first difference? It's going to be minus 8. Just to check, let's do the next one. That's also going to be minus 8. Okay, so Tn is going to be minus 8n. That's our difference. Plus b, we don't know what that is yet. But we do know the first term is 25. So we can use that. So 25 is equal to minus 8 times 1, because we're taking the first term, plus b. Okay.
Sorry, Brandon.
Yes.
When you have completed question 3, there are 2 questions in the chat. I think they're from question 1 and question 2. So maybe before you continue to question 4, like once you've completed this question, maybe you can address them so that the students understand.
Sure. I think I missed those. Let me have a look.
I think he's already addressed them.
Have you, Rachel?
I don't.
Yeah, Brandon addressed them right after he finished question 2.
Okay, all right, that's good. All right, thank you.
Okay, so we substitute in 1 because that's our first term here. So let's just write that down here. So we're taking T1 is equal to 25 with n is equal to 1. So we want to find b. Okay, so we just take that across, 25 plus 8, that's going to be b. Sorry. So b is equal to 33. So let's just sub this back in so we complete our formula. So Tn is going to be minus 8n plus 33. Okay, so we've got our equation now. So we still want to find when is this less than minus 55. If we go back here, we've got Tn, we know what that is now. We want this to be less than minus 55. Okay, so let's substitute that in. So we want Tn to be less than minus 55. So Tn is minus 8n plus 33 is less than minus 55. So minus 8n is going to be less than minus 55 minus 33. We just took that across. Okay, so minus 8n, minus 8n is less than minus 88. Now, big warning here. Okay, I hope everyone knows this, but when you multiply through by a negative and you've got yourself an inequality, the little inequality sign will flip. So if minus 8n is less than minus 88, then n is going to be greater than 11. Okay, so always keep that in mind when you're multiplying inequalities by a negative, or if you're taking reciprocals, your inequality is going to have to flip. Okay, so we see here that n has to be greater than 11. Now, let's just check some values here. So if Tn, okay, so if n is actually equal to 11, what do we get? So that's going to be minus 8 times 11 plus 33. That's going to be, so we have minus 8 times 11, minus 88 plus 33. That's going to give us the minus 55. But notice this is equal to minus 55. Okay, we wanted something that was strictly less. So we can't include 11 because that gives us equality. So it must be 12. So from 12 onwards. So the smallest value would then be at 12. Okay, so always do that little check. Just because you've got an 11 there doesn't mean you start from 11 in that case. We need the integer bigger than 11. Okay, so that's going to be 12. Okay, let's see if there's any questions here. No. Okay, so I hope that's not too bad. Next one, 3.2. Okay, so now we've got some summations mixed in with patterns. So we've got the sum from k equals 1 to 6 of x minus 3k. Now we don't know what x is. That's an unknown for now. That is equal to the sum from k equals 1 to 9. Again, we've got this x. We don't know what that is. Minus 3k. Prove that the sum from 1 to 15 of x, again, there's that x, we don't know what that is, of x minus 3k is equal to 0. Okay, so the key here is that it says, given that this stuff over here. So this is our starting point. Or it's the clue. However you want to think about it. It's some information that's given to us that we need to prove something else. So we better start off with that and see what more information we can get from that. Once we've got that extra information, then we can start to tackle the main problem of proving this little expression over here. Okay, so don't skip when it says given that something. Okay, we need to use that to our advantage. Okay, so let's go ahead and do that. So we start off with the fact that the sum from k equals 1 to 6 of x minus 3k is equal to the sum from k equals 1 to 9 of x minus 3k. Okay, what can we do with this? Well, the summation on the left-hand side goes up to 6. The summation on the right-hand side is exactly the same. Okay, all the inner workings is exactly the same, except now it's going up to 9. In other words, the right-hand side has a few more terms than the left-hand side. Okay, which means they're pretty much equal except for a few terms. So let's see what those are. Okay, so the left-hand side, that's still k equals 1 to 6, x minus 3k. And then on the right-hand side, we can make this look a bit more like the left. So we can have the sum from k equals 1 to 6 of x minus 3k. Plus, we've got some extra terms, because remember, the right-hand side goes up to 9, not 6. So what's missing? We're missing x minus 3 times 7 plus x minus 3 times 8 plus x minus 3 times 9. Those are the terms missing from the summation up to 9. That's the 7, the 8, and the 9. But everything else is equal. And since it's equal, we can just cancel it. So the two summations there go away, and that becomes 0 is equal to x minus 3 times 7, we can just write 21. X minus 3 times 8, we can just put it 24. And x minus 3 times 9, we can put it 27. So much simpler than that whole sigma notation that we started off with. Now we can simplify this a bit more and then solve for this x that we didn't know. Okay, so we've got 3 x's, we can take that over. And that's equal to 72. In other words, x is just 24. So we know the value of x now, and we can use that to just substitute into this expression I put a box around. Because we know the value of x, we know how to sum things up, so we can just sum it up and check that it's equal to 0. So let's go back down here. So we know x, so that means the sum from k equals 1 to 15 of x, but that's just 24, minus 3k is equal to, it's just the sum. And we know that there's a nice formula for sums. It's n over 2, 2a plus n minus 1 times d. Right, where n, that's the number of terms. D, that's our difference. And A, that's our starting point. So we know all of those. So let's plug them in. So we're going to have 15 over 2, 2 times 21, plus 15 minus 1, so that'll be 14. And our difference is minus 3. Yeah, there we go. Minus 3 there. Okay, so a little bit of work. We see that this is 15 times 21, and then minus 15 over 2 times 14 times minus 3. Well, 14 over 2 is 7. 7 times 3 is 21. We end up with 15 times 21 as well. But that's just going to be 0. Okay, and that's it. So always remember, use what's given to you. So it doesn't matter if it seems really weird. Take what's given to you, work with it, and see if you can find something that's useful. Like in our case, we were given that these two sums were the same. Now we can use that to find out what x is. Okay, once we know what x is, we can substitute it in and then just evaluate the sum directly. Okay, so always use what's given. It's always extra information to help you out. And also, it's very useful to know your summation formula. Okay, so if you've got yourself an arithmetic sequence, we can use the summation formula to find the sum up to n. Okay, so that's always good to remember as well. Okay, so as before, if you have any questions, please let us know in the chat. Okay. Okay, so I hope everyone's following along so far. Really not too bad. Okay, yeah, so the worst thing that you can do is panic when you've got these pattern questions. Maybe you don't see the pattern right away. Like I said, write out a few terms if you need to, just get a real understanding of what's going on and what tools you can use to move forward. So whether that's your summation formula or your TN formula for geometric, just have all of those in mind so that you can move forward. Okay, but if you don't know your formulae, then you're really stuck. Okay, so please go over those formulae and those expressions. Okay, next bit. So consider the quadratic sequence. Okay, so it's quadratic. So the first thing that should pop into your mind is the sequence has a first difference, it has a second difference, and that second difference is constant. Okay, always keep that in mind. 2.1.1. Determine Tn if the nth if n is the nth term of the quadratic sequence. In other words, just find the general pattern. Okay, so that's not too bad. So 2.1.1, 72, 100, 120, 132, and so on. Now we know it's quadratic, which means we have to find the first difference and the second difference. Okay, so the first bit, we get 28, then 20, and then 12. Okay, we're not convinced yet that it's quadratic, so we find the second difference. We get -8, we get -8. Okay, so now I'm convinced. We've got a constant second difference. We can use that. And remember our important terms. It's going to be this one, and this one. So those terms along the diagonal is what we use to find A, B, and C. So we start off with A. 2A is equal to -8. So A is going to be -4. 3A plus B is going to be 28. So we're going to have -12 plus B is equal to 28. So B is equal to 40. And again, a little bit of warning. Remember, when you're finding B, it depends on A. When you're finding C, it depends on A and B. So please check your working at each step so you're not substituting wrong answers to find the next term. And lastly, A plus B plus C, that's going to be our yellow term, which is 72. So A was -4, B is 40, C, we don't know, and that's all equal to 72. So C is equal to 36. Okay, so we've got A, B, and C. So we're going to have Tn is equal to an squared plus bn plus c in that order. A is -4, so we get -4n squared. B is 40, so we get plus 40n. And C is 36, so that's just 36. Okay, so we get ourselves our Tn formula. Okay, so not too bad. Next, a term in the quadratic sequence, okay, so that's the sequence we've been working with, is equal to the 12th term of the sequence of first differences. Okay, that's quite a mouthful, but what does that actually mean? So we've got a term, and it's equal to the 12th term of the first difference sequence. So that's the second one over here, this line. So if we consider the second line as its own sequence, then what we're looking for is the 12th element of this one. Yeah, because that's what we mean by 12th element of the first difference sequence. That's the second row, the 12th term. Determine the position of this term in the quadratic sequence. Okay, so this is in two parts. So first we need to find out what the value is. And secondly, we then need to find its position. In other words, n. Okay, so it's a two-part kind of question. Okay, so let's take a look at part one and find the 12th term of this first difference sequence. So 2.1.2. So the first difference sequence we can write as 28, 20, and 12. And now we just treat it as an arithmetic sequence because that's what it is. And we see that this goes -8, -8. Now, I'm not going to call this Tn, okay, because we've already used Tn. Let's call this Dn, D for difference. So that's going to be -8n plus b. We don't know what b is. But we can use the first term here to work that out. So 28 is equal to -8 plus b. So b is equal to 36. Okay, that's good. So we know dn is equal to -8n plus 36. Okay, so we're getting there. Now, remember the question said it was the 12th term in the sequence. So we need to find B12. So that's going to be -8 times 12 plus 36. That's going to be -60. So this is our Tn that we were looking for. However, we're not done yet. We know the value of Tn, but what they wanted was the position, not the value. So if we go back here, it says determine the position of the term. So we still need to find n. But that's not too bad. We've got Tn, we've got the formula for Tn, and we've got the value for Tn. So we can use that to work out n. So Tn is equal to -4n squared plus 4tn plus 36. We worked that out earlier. This must be equal to -60. And what we really want is n. Okay, we want to find out what that is. Okay, that's not too bad. We can just take everything over to one side and solve it just as a quadratic, right? Just in this case, n is an integer. rather than some real number x. So we have minus 4n squared plus 40n, and then 36 plus 60. So that's going to be plus 96. Okay, is equal to 0. Okay, so now we need to divide through by minus 4. So we're going to have n squared minus 10n minus 24 is equal to 0. We can factor this into two parts. We're going to get one solution, which is going to be negative, so we throw that out. We get another solution that's positive. Okay, we get another solution that's positive. We need to take that one. So in this case, we get n equals minus 2, n equals 12. We don't want negative n because n has to start from 1. So the term is at position 12. Okay, so just a little note, we throw out negative solutions. Right, because n must be a natural number. We can't have negative values of position. Okay, so a bit more working than usual, but as long as you follow each of the little sub-steps that we set out, it's really not too bad. Okay, so whenever you have like this big question where it's like the whole question's quite a mouthful, break it up into smaller things that you can work on. So we're given that this term is the 12th term of the sequence of first differences. So we know that we should be looking for the formula for this pattern of first differences. Because once we know the pattern of first differences, we can find the 12th one. And then once we have that, then we can move on and find the position of this term in the original quadratic. Okay, so if you try to do everything at once, it's hard to keep track of what you're doing. But if you break it down into little steps, manageable steps, then you can get your answer. Okay, 2.1.3. Determine the maximum value of the quadratic sequence. Okay, so we want the maximum value. Now, the quadratic sequence, we know Tn, it's something n squared plus bn plus c. It's a parabola, right? Because we've got n squared there. So if we want to find the maximum value of the sequence, that is the same thing as finding the maximum value of the parabola. Right, because Tn is a parabola, it's something n squared. So if we can find the maximum value of the parabola, we get the maximum value of the sequence. Now, how do we find the maximum value of the parabola? Well, the maximum value of the parabola occurs at the turning point. So what we need to do is find the turning point of the sequence. Yeah, we found the turning point. We've got ourselves the maximum value. Okay, so let's have a look at that. Okay, so we've got Tn is equal to minus 4n squared plus 40n plus 36. Now, this is what's usually called standard form. You've got your an squared plus your bn plus your c. However, to find the turning point, we would rather write this in the turning point form. Remember, it's your a, n minus p, all of that squared plus q. Now, how do we get from your standard form to your turning point form? We need to complete the square. So if we complete the square, we've got ourselves the turning point. So let's go ahead and do that. So Tn is minus 4n squared plus 4tn plus 36. Okay, so to complete the square, there's a number of steps you need to follow. The first thing is we need this n squared and the n, those two terms, we need them by themselves. So we can do that by factoring out this minus 4. So we have minus 4 into n squared minus 10n, and then we can add our 36. Don't forget to carry your constant term down. You don't want to forget that on a previous line. Next, we look at this term, our bn term. We see what that value is. In this case, it's minus 10. We divide it by 2. That's going to give us minus 5. And we put that alongside our n in brackets. So we get minus 4, n minus 5, and then we square the whole thing. Now, the reason we did that is because if we then square this out, we're going to get n squared minus 10n, but we're also going to get plus 25. But that's a problem. On the previous line, we didn't have any plus 25, but on this new line, if we expand this out, we're going to get an extra, emphasis on the extra, plus 25. So we need to take care of that. So what we do is we minus this 25. And then don't forget your plus 36. Okay, so just to reiterate, this 25, where did that come from? That came from the 5 squared term, or in our case, it's going to be the minus 5 squared term, but that's the same as 5 squared. That's 25. Right, from our binomial expansion. We never wanted that term, so we need to subtract it off again. Okay, so let's multiply this out. So we get minus 4, n minus 5 squared, plus 100, plus 36. So we get minus 4, n minus 5 squared, plus 136. Okay, so now that it's in our turning point form, we know that the turning point happens when n is equal to 5. And this term here, this is our maximum value. Yeah, so technically speaking, it's the y part of the turning point, but since we're looking for the maximum value, that's exactly what we're looking for. So the maximum value of Tn is going to be 136. Okay, so just a little bit of advice for this. If you're ever given a quadratic sequence and you want to find the minimum value of the sequence, or you want to find the maximum value of the sequence, those always correspond to the turning point of the parabola. Whether the turning point is the maximum or the minimum, that doesn't matter. In either case, we're looking for the turning point. Okay. So you write your quadratic formula, so your an squared plus bn plus c. You write it as a turning point form, okay, like we've done here. And then whatever your constant is on the end, that's your maximum or your minimum, depending on what you're looking at. Okay, but it's always completing the square. That's the tool to solve this problem. All right, as always, if you have any questions, please leave them in the chat. Okay, so we'll just do this last one here, and then we'll take a break for a little bit, and then we will carry on with functions. Okay, so just a short little break. You can grab some coffee or tea or something like that. So 2.1.4, determine the maximum value of this sequence. Okay, so again, we want to find the maximum value. But if we look at the sequence here, it looks familiar. Okay, we've got minus 23, 5, 25, 37. Maybe you don't see it right away. Okay, but let's go through it. It should become obvious pretty soon. Okay, so 2.1.4. We've got minus 23, 5, 25, 37, and this carries on. Let's see what kind of pattern it is. Maybe it's something completely different. We see we get 28, 20, and 12. Okay. And then for the second difference, we get minus 8, minus 8. That looks very familiar. Let's go back to what we had before. Okay, we've got this here, the one with 72, 100, 120. Look at the first difference and look at the second difference. It's exactly the same as this. So this new pattern has the same first difference and the same second difference. So it's exactly the same pattern, except it's been shifted down. So originally, if we go back up, yep, originally the pattern started at 72, but now the pattern starts at minus 23. We've just shifted all of the terms down. Okay, it's exactly the same pattern. We've just shifted down a bit. So the amount we shifted down from 72 to minus 23, that's going to be 95. So if all of the terms have been shifted down by 95, well, then so has the maximum. So we could just write that the maximum of this sequence is the maximum of the previous sequence, but minus 95. Okay, now if you don't notice that, that's perfectly fine as well. We can go through the full working and we should get the same thing. Okay, so let's say we didn't notice that, that pattern between these two and just treat it as a whole new pattern. Okay, that's fine. So we got our minus 8, our 28, and our minus 23. Okay, so we're just going to treat this as a new pattern given to us. So 2a is going to be minus 8, a is going to be minus 4, 3a plus b is going to be 28, and we know what a is, so we're going to have minus 12 plus b is equal to 28, b is equal to 40, okay, same as before, and then we have a plus b plus c, and that's going to be our yellow term, which is minus 23, a is minus 4, b is 40, c we don't know, that's minus 23, so c is going to be minus 59. Okay, so we see a and b are the same as before, but c has been shifted. Okay, that's exactly what I was talking about. Everything has just been shifted down. So Tn is going to be minus 4n squared plus 40n minus 59. We want to know what the maximum value is. So again, we just complete the square, exactly the same as last time.
Complete the square.
Okay, so we complete the square. That will give us our maximum value or the turning point. And we see that the new maximum is equal to 41. So you can go through all that work on completing the square, or if you did notice the relationship between the two patterns, we could just say that the new maximum is the old maximum of 136 minus 95, because that was the difference between the terms. And that's 41. Okay, so either way, we get the same answer. Okay, so we're going to take a break for a few minutes. I think we should start again at 5 past. So you can go grab a drink or something to eat. If you do have any questions in the meantime, please put them in the chat and then we can have a look through those. Okay, you can go grab something to eat or get some water. Okay, we'll start shortly.
Brandon, can you please make me co-host?
Sure.
I got kicked out by network and I lost my abilities.
Sure, there we go.
Thank you so much.
Sure, no worries. Okay, so just while we're waiting in this break, if you do have any questions, please put them in the chat. Questions related to what we're covering now, please. If you do have other questions, there is a dedicated email line. You can ask any question you like over there, and then we can get back to you on that.
I think to fill up the space during the break, can I please play the video that the varsity has asked us to play? It's a 3-minute video. I don't think it's going to go over the break time, if that's not a problem.
Sure. Yeah, please go ahead.
Thank you so much.
With future game changers and leaders. They do say that the extent of one's success can be attributed to those they rub shoulders with. Therefore, you must surround yourself with like-minded people. So, how do you become part of a community that is committed to your self-development? How do you become part of UKZN? First, you have to apply. All applications for undergraduate studies at UKZN are processed through the Central Applications Office, CAO. This is for both your course and student resident application. The application process is as follows. Step 1. Consult the CAO handbook. This handbook provides a list of all qualifications available at UKZN. Step 2. Have a look through the various courses offered and choose a program that interests you and for which you meet the minimum requirements. As one of the top 5 universities in the country, UKZN promotes academic excellence. So meeting the minimum requirements does not guarantee you a place to study. Step 3. Find the program code linked to your chosen qualification. This is the code you need to enter in your application form. Okay, let me show you something. You see, a code has 3 parts. Example, for BCom in accounting, the code is KN-P-BCN or KN-W-BCN. Crazy code, right? Well, basically, the KN stands for UKZN, the middle part stands for the campus of your choice, P for Pietermaritzburg, W for Westville. Then, BCN stands for the actual course. Make sure to get these codes right. Step 4. Use this program code when completing your CAO form, which is available from the CAO website. Your application will be sent to UKZN. You can always check the status of your application using your CAO number, ID number, or passport number on this website, www.caocheck.ukzn.ac.za. For more information, visit www.cao.ac.za. It's that easy. Pay close attention to closing dates for qualifications. For example, MDCHB closes on the 30th of June, while other undergraduate programs close on the 30th of September. What are you waiting for? Apply now and shape your future today.
Hello, everyone. Welcome back. I hope that was enough time to grab some water, a little bite to eat. So I think we're all pretty tired of patterns now. So let's take a look at some functions. Okay, so I've got a few questions on functions here. So we've got ourselves an exponential function, g of x is equal to 1/2 to the x. So for 4.1, write down the range of the function. Okay, well, we can do a little picture of this first. So 1/2 to the x, we could write this as 2 to the minus x. So this is going to be something like this. Okay, where on the right-hand side here, the function goes down to 0, and on the left-hand side, the function goes up to infinity. But in either case, we see that the function is always above the x-axis. Okay, it's always positive. So here we see that the function is always positive, and so the range is always positive. So the range is y is greater than 0. Now, there's a number of ways of writing the range. We could say y is an element from 0 to infinity, or we can say 0 is less than y, less than infinity, anything like that. Okay, whatever kind of set notation you want to use, they're all equivalent, as long as you get the idea that the y value must be greater than 0. Okay, so 4.2, determine the equation of G inverse. Okay, so we've got G, we would like to find the inverse function. So let's have a look at that. So the way we do that is we write down our function. So we have y is equal to 1/2 to the x. Now, to find the inverse, we swap x and y around. Okay, so we're going to swap x and y. So we have x is equal to 1/2 to the y. Okay, so we just did a little swap of x and y. Okay, so with that in mind, we can then now solve for y. Okay, so how do we do that? Well, y is in the exponent. So how do we get it down from the exponent? Well, we need to take the log on both sides. So if x is equal to 2 to the minus y, then if we have log base 2 of x on the left-hand side, log base 2 of 2 to the minus y on the right-hand side, then that will clear our base. So we're going to have log base 2 of x is equal to minus y. Or in other words, y is equal to minus log base 2 of x. Okay, this is our G inverse that we were looking for. Okay, if you have any questions, please put them in the chat. 4.3. Is G inverse a function? Justify your answer. Okay, well, G inverse is the log function. So yes, G inverse is a function. Now, why is it a function? because G inverse takes one input, okay, your value of X, and sends it to one output. Okay, and that's what functions need to do. They take one input and they send it to one output. Now, if it took one input and sent the same input to two different outputs, then that's a non-function. Okay, we're not interested in those. Since this takes one input to one output, it is indeed a function. Okay. In other words, it satisfies that vertical line test, if you want to phrase it like that. Okay, but whether you want to say a vertical line test or you want to say sends one input to one output, it means exactly the same thing. Okay, 4.4. We've got a point M that is A comma 2 lies on G inverse. Calculate the value of A. Okay, that's not too bad. So we have 4.4.1. M is given by A comma 2, and it lies on G inverse. And we've just calculated that. Okay, so what we can do is substitute this point into our equation for G inverse, and then we can solve for A. So y is equal to minus log base 2 of x. We've got x, that's A, and y is 2. So 2 is equal to log base 2 of A, minus log base 2 of A. We want to know what that is. So we have minus 2 is equal to log base 2 of A. So A is going to be 2 to the minus 2, or we can just have 1/4. Okay, so that's one way of doing things. Another way is by noticing that G inverse of A is equal to 2. Okay, again, we just substituted the point in. Now we can apply G on both sides. So G of G inverse of A is equal to G of 2. Okay, so let's just color code this. So we've got G, and on the inside, we've got ourselves G inverse. Now remember, functions and their inverses, they cancel each other out. So G of G inverse of A, or the G and the G inverse go away, we're just left with A. And that's going to be G of 2, which is 1/4. So that's another way of looking at the same problem. Yeah, but we get the same answer in the end. Okay, let's have a look at some of these questions here. Okay, no questions on this. Okay, so that's 4.4.1. Let's have a look at 4.4.2. We've got M prime is the image of M. Okay, so M prime, it's the image of M that lies on G. Write down the coordinates of M prime. Okay, so we know that M lies on G inverse, which is the inverse of G, and M prime is the image of M. So it's the corresponding point that lies on the other graph. So if M is given by A comma 2, remember A is 1/4. So we have 1/4 comma 2. And now we want to find the image on the inverse function. Remember what we did to find the inverse. We swapped X and Y. So if we want to find the image, we just swap X and Y. Okay, as easy as that. So when going from a function to its inverse, we swap X and Y. If we're going from a point to the image of the point on the inverse, again, we just swap X and Y. Okay, pretty simple stuff. Okay, 4.5, a little bit more complicated. We've got h of x is equal to g of x plus 3, and then plus 2. Now, what does this mean? What does this x plus 3 mean? And what does this plus 2 mean? Well, the x plus 3 means that we took our original function and we shifted it to the left by 3. Okay, right. If you got a plus, you go to the left. If you got a minus, you go to the right. And this plus 2, this means we shift up by 2. Okay, so h is g, but shifted to the left by 3 and shifted up by 2. Now we want to know what are the coordinates of the image of m prime on h. So we've got ourselves m prime. Okay, we know what m prime is. We worked that out here. We want to now know the image of m prime on h. So it's like the double image. So 4.5. We've got m prime. Let's write that down again. That's 2 1/4. And what do we do to get from this to the target point after the shift? We shift left by 3 and up by 2. Yeah, that was our translation from m prime to now m double prime. Okay, so it's going to be shift to the left by 3, so 2 minus 3, and shift up by 2, so 1/4 plus 2. So m double prime, 2 minus 3, minus 1, and then 1/4 plus 2, we can write that as 9/4. Okay, so we just need to follow our shifting rule over here. Okay. Any questions on that? Okay, cool. Okay, so that's it for this question. Let's have a look at the next one. Okay, so we got f is 1/x plus 2 plus 3. So it's a hyperbola that's also been shifted. It's a shifted hyperbola. Okay, 5.1.1. Determine the equations of the asymptotes of f. Okay, so 5.1.1. Now the asymptotes, there's 2 of them. We've got the horizontal asymptote. Okay, that's going to be given by this plus 3 over here. Okay, because we shifted up by 3. The original asymptote was at y equals 0. Now we shift up by 3, so the horizontal asymptote is at y equals 3. And the vertical asymptote okay, well, that's when this denominator goes to 0. Because when the denominator is 0, 1/0, that blows up to infinity. So x plus 2 must be 0. So x is minus 2. Okay, so we've got our horizontal asymptote. That's the y part. We've got the vertical asymptote. That's your x part. Okay, good. 5.1.2, write down the y-intercept of f. Okay, so if we want to find the y-intercept, that means we let x be 0. Okay, you let x be 0, you get the y-intercept. So we're going to have y is equal to 1 over x is 0, so 0 plus 2 plus 3. So that's going to be 1/2 plus 3. That will be 7 over 2. Okay, easy stuff. 5.1.3, calculate the x-intercept of f. Okay, so 5.1.3, x-intercept. Now, in this case, we want y to be 0, okay, because we want the x-intercept. So if y is 0, then we get 0 is equal to 1 over x plus 2. We want to find out what x is, plus 3. We take the 3 over, we get minus 3 is 1 over x plus 2. We can take the reciprocal on both sides. So we get minus 1/3 is equal to x plus 2. We take the 2 across and we end up with minus 7 over 3. Okay, so that is our x-intercept. So minus 7 over 3 and 0. And another one, we could write this as 0 and 7 over 2. Okay. So everything's pretty straightforward so far. Last question here. Calculate the sketch the graph of f. Clearly label all intercepts with the axes. Okay, so your x and y intercept and any asymptotes. So that's the first two things we found here. Okay, so let's have a go at sketching this. So this is 5.1.4. We've got our XY plane. This is a positive number in the numerator. So we know that it should be taking up the first quadrant and the third quadrant. Okay, so just keep that in mind with the sketch. We know that it's been shifted across to the left and it's been shifted up. So it's going to look something like this. Sorry. Let's do that a bit better. Something like that. Okay, let's actually just rub this out. Yeah, there we go. That's a bit better there. Okay, so we've got ourselves the vertical asymptote here. We've got ourselves the horizontal asymptote here. And usually the asymptotes are given by dashed lines. Okay, so we don't confuse them with the functions. Okay, so the vertical asymptote, that was at x equals minus 2. The horizontal asymptote, that was y equals 3. The y-intercept over here, remember that was 7 over 2. So it's 0, 7 over 2. And this other one, the x-intercept over here, that was at minus 7 over 3 and 0. Okay, that's everything that we need to label there. Okay, I've got a question here. You thought vertical was y and horizontal was x. So x does go along horizontally. However, for a fixed value of x, we get a vertical line. So let's say we have x equals 1. That's over here. X equals 1 actually corresponds to this line. It's a vertical line. Like that. And if we look at a fixed y value, so let's say y equals 2, this actually corresponds to a horizontal line. Like that. So that's why we call it vertical asymptote and horizontal asymptote. It's because the lines are actually vertical lines for x. And they're horizontal lines for y. Okay, so that's where the names come from. For a fixed x value, you got yourself a vertical line. for a fixed y value, you got yourself a horizontal line. And so that corresponds to the naming of the asymptotes as well. Okay, I hope that answers your question. Okay, let's move on. Okay, we've got ourselves a parabola given by K and a straight line given by H. Okay, so let's just highlight that. We've got a parabola there. We've got a straight line there. Okay, it's always good to underline or highlight the information given to you so you can quickly see it for later. And we've got a turning point at -1 and 18. That's for our parabola. That's over here. Okay, S is the X intercept of H and K. So that is this point over here. Okay, so that's all the information given to us there. And they also intersect at T. Okay, so that's everything that's important. 5.2.1, calculate the coordinates of S. Okay, so we could try and calculate S as one of the X intercepts of K. That's not going to work out too well because we don't know the values of A, B, and C. Okay, so we don't know what K is. However, H is given to us. So we can use H to find S. So 5.2.1, we know H of X is given by -2x plus 4. We want to know what happens when y is equal to 0. So we have 0 is equal to -2x plus 4. -4 is equal to -2x. So x is going to be 2. Okay, so if x is 2, we know that S is given by 2, 0. Okay, not too bad. 5.2.2, determine the equation of K in the form y equals A, x plus P, all of that squared plus Q. In other words, this is our turning point form. Okay, so we got ourselves the turning point form. That's useful because we know what the turning point is. We've got the turning point here at -1 and 18. So we can use that to find K. So 5.2.2, K of X is equal to A, X plus P, all of that squared, plus Q. But we know what the turning point is. So we know the values of P and Q. So K of X is equal to A, X plus 1 squared plus 18. Okay, because we know what all of those values are. And that's a plus 1 there. Okay, but we still don't know what A is. That's kind of the problem here. We don't know what A is. However, we do know what S is. And S is also a point on the parabola. We see that it's one of the X intercepts. So we can substitute in S and then solve for A. So we sub in S and then we can solve for A. So the Y value is going to be 0. And the X value is 2. Okay, so we get 0 is equal to A times 2 plus 1, that's 3 squared, that's 9, plus 18. So -18 is equal to 9A. Divide by 9, A is equal to -2. Okay, so we got everything we need now. So this means K of X is going to be -2 X plus 1, all of that squared, plus 18. Okay, and we've written it in turning point form, which is what they wanted. 5.2.3. Okay, so now they give us the full expression for K in standard form. Determine the coordinates of T So T was the intersection of K with H. Now, intersection means that they're equal at that point. So we better have that K of X is equal to H of X. Okay, that's how we can find the intersection. Okay, so K is given to us. That's minus 2x squared minus 4x plus 16. H of X, that was given to us at the top, minus 2x plus 4. We highlighted that in blue. Okay, looks a bit messy, but if we take everything over to one side, we're going to get minus 2x squared minus 4x plus 2x, that's minus 2x, plus 16 minus 4, that's going to be plus 12. Okay, we can divide through by minus 2 just to make things a bit simpler. So we have x squared plus x minus 6 is equal to 0. Okay, and then we can factor this now. Okay, so we're going to get x plus 3 and x minus 2 is equal to 0. So that's just factoring the quadratic there. So we're going to get two solutions. We're going to have x plus 3 is equal to 0. So x equals minus 3. And we're going to have x minus 2 is equal to 0. So x is equal to 2. Okay. Now, which solution corresponds to the thing that we want? So if we go back up to our picture, we see that one of the solutions will be t, that is on the left-hand side. The other solution will be s, that's on the right-hand side. So if we look here, we see that this x equals 2, this corresponds to s. And the x equals minus 3, that corresponds to t. Okay, so we're not interested in the s solution. So the x component of t is going to be minus 3. What's the value for y? So if x is equal to minus 3, then y is going to be, well, we can substitute it into either expression, doesn't matter. Let's substitute it into the line. So we have minus 2 times minus 3 plus 4. That's going to be 10. So altogether, t is given by minus 3, comma 10. Okay, so that's the coordinate t. Okay, 5.2.4. Determine the value or values of x for which k of x is less than h of x. So where is our parabola below the straight line? Okay, so let's have a look at that. So we want k of x to be less than h of x. We know what k of x is. That's going to be minus 2x squared minus 4x plus 16. That is less than h of x. That's minus 2x plus 4. Okay, again, it's a bit messy like this, but let's take everything over to one side. So we're going to get minus 2x squared minus 4x plus 2x plus 16 minus 4. All of that is less than 0. Okay, so after simplifying through, we're going to get x squared plus x minus 6 is going to be greater than 0. Okay, because when we divide through by minus 2, our inequality sign flips over. Okay, so whenever you multiply through by negative, the inequality sign flips. Whenever you take the reciprocal on both sides, the inequality sign flips. Okay, so please keep that in mind. Okay, so we need to find the so-called critical values of this. In other words, where is x squared plus x minus 6 equal to 0? We're going to get two solutions for that. We're going to get x equals minus 3 and x is equal to 2. Now that we have those two, we can plot them on a number line. So the minus 3 comes first, and the x equals 2, that comes second. Okay, it's got to be in ascending order like that. Next, we look at the quadratic we've got. It's x squared, so positive x squared, which means it is a happy face parabola. So it looks something like this. Now, what we want is to find where is the parabola positive. Well, that's going to be on this side, it's positive. In between, it's negative because it's below the x-axis. And then after x equals 2, it's back to being positive. So we're interested in the far left part before minus 3 and the far right part after x equals 2. So we are interested in the x values that are less than minus 3 or the x values that are greater than 2. Now, they're not equal because if we look back at our inequality thing we've got here, it is strictly greater than. So we're not including those points. If it was greater than or equal to, then of course in our answer we would write equal to as well. Okay, but it's a strict inequality, so our solution also has this strict inequality here. Okay. Or another way of writing this, we could say x is an element of minus infinity to minus 3, union, to go with the or, to comma infinity. Okay, that's just another way of writing it, but other way, we're saying the same thing. Okay, let's have a look at the questions here. Okay, I've got a question here, x equals minus 2 and x equals 3, because the coefficient of x is 1. Yes, that's right. Sorry. Yeah, so coefficient is 1, so we can just factor it as x plus 3, x minus 2, and then we get our two roots of minus 3 and 2. Okay, so if you want to put in the in-between step, we can write this as x plus 3, x minus 2. Okay. But we're interested in our two roots over here. Okay, I think that were all the questions here. Yes, okay. Let's have a look at the next bit. Okay, so that was 5.2.4 done. 5.2.5. It is further given that K is the graph of G prime. Now, when they say G prime, what they mean is the derivative of G. So this over here, this is the derivative or the gradient of G. Okay, so K of X is the gradient of G. So 5.2.5a, for which values of X will the graph of G be concave up? Okay, so we're dealing with concavity now. So remember, concavity is with the second derivative. So we've got the first derivative, we need to find the second. Okay, so let's have a look at that problem. So this is 5.2.5. So it's given that K of X is equal to G prime of X. However, when we're dealing with concavity, we want G double prime. Okay, G prime gives us the gradient, G double prime gives us the concavity. So G double prime of X, that's going to be K prime of X, that's going to be minus 4X minus 4. Okay, so now we want to know, where is it concave up? So concave up is the same thing as asking, where is G double prime greater than 0? Okay, so we want this to be greater than 0. So we want minus 4x minus 4 to be greater than 0. So we want 4x plus 4 to be less than 0. In other words, x is going to be less than minus 1. So it is concave up on the interval minus infinity up to minus 1. Okay, on that interval, we have that this function g is concave up. And then if you wanted to know where it was concave down, you would just have to flip the inequality to check where it is less than 0. So for concave down, if you're interested in that, that's going to be g double prime of x is less than 0. Okay, so they go hand in hand. Concave up, double derivative greater than 0. Concave down, double derivative less than 0. Okay, let's have a look at the next bit. Okay, so for part B, we want to sketch the graph of G, showing clearly the x values of the turning points and the points of inflection. Okay, so we've got a bit of work to do. We want to find the turning points and we want to find this point of inflection. Okay, that's not too bad. So this is part B. Part B. To find the turning points, we want the gradient to be equal to 0 because the tangent line will be flat and we get our turning points at those locations. So we want g prime of x to be equal to 0. So g prime, remember that was k, so it's going to be minus 2x squared minus 4x plus 16 is equal to 0. Okay, in other words, we want the roots of this. Okay, so we can factor this or divide through by minus 2 and then we can factor. We end up with x plus 4, x minus 2 is equal to 0. Okay, so this is going to give us two solutions. The first part is when x plus 4 is equal to 0. So when x plus 4 is equal to 0, x is going to be minus 4. For the second part, we have x minus 2 is equal to 0. So x is equal to 2. Okay, so those are our two turning points. We've got one turning point at x equals minus 4. We've got another turning point at x equals 2. Okay, what about the points of inflection? That's going to be g double prime is equal to 0. So remember what I said earlier, when g double prime is positive, we're dealing with concave up. When it's negative, we're dealing with concave down. When it's equal to 0, we call that the point of inflection. Okay, so that's easy enough to do. We've got minus 4x minus 4 is equal to 0. So x is equal to minus 1. Okay, so we've got the two turning points and our point of inflection. Okay, so we have x and y. So we've got a turning point at x equals minus 4. So let's say it's going to look something like this. Okay, so here at x equals minus 4, we've got a turning point. over here at x equals 2, we've got a turning point. And then somewhere in between, the graph flips from being concave up to being concave down. That is our point of inflection at x equals -1. Okay, and just a little bit of extra on this left-hand side here, this is going to be concave up. And then on the other side, this is going to be concave down. Okay, now you don't need to include that in your sketch. That's just so that we can see the difference between the two sides. Okay, so they're different about this inflection point. So to the left of the inflection point, concave up. To the right of the inflection point, concave down. And then we've got our two turning points as well. Okay, so this is the graph of G. Okay, any questions on that? Okay, no questions there. I think we can leave it at that for today. I don't think we'll have enough time to go through the next problem. So that's going to be it for today. For the next session, we are going to be going through maybe a bit more of functions, and then we'll go through some finance. Okay, so that's the next part. And then that will be enough for your paper 1 coming up. And then for your paper 2, we have the session on Saturday. Okay, and that's where we will be going through all of your paper 2 material. Okay, so if you want to just plan around that. Okay, so next session tomorrow, we're going to finish the stuff for paper 1. And then on Saturday, we're going to be finishing the stuff for paper 2. Okay, yes, I see in the chat there, if you just want to have a look, there are the times for the remaining sessions. Okay, so just to go over it again, next session tomorrow, we finish the stuff for paper 1. Then on Saturday, we finish the stuff for paper 2. Okay, if you do have any questions after this, please feel free to use that email address. It's on the poster. It's just a hotline. You can send all your questions there, and then there will be someone that can help you with that. Okay, but thanks to everyone for coming. I hope to see all of you next time.
Thank you, guys. Before you leave, please remember to do the survey that has been put in the group. It will really help us improve in terms of the sessions that we are having. Thank you so much. See you all tomorrow morning.
Thank you, thank you, thank you. La la la, hey.